main tasks in machine learning is the one is classification. This asks the question in which class is a given object, is a given individual, and the second one is regression, which asks the question which target value belongs to an object. So, for example, which age will this individual has, or how long does it take to until some event occurs? Yeah, this is some number that the algorithm gives out. And the data set that is used as an input is usually divided into a training data set that is used for training. This is training the predictor. The predictor is the model, kind of an algorithm that gives the prediction, that solves the task. And this model needs to be trained by the training data set. And then it can be validated with the validation data set, and the model can be updated from what we've learned from the validation data set. So some hyperparameters, it's called, can adjust the model, can be updated. And this is usually 20% of all data. And then we have a test data set, also 20% of all data that should never be touched until the end. And this is used because machine learning is kind of a black box. You don't know exactly why the algorithm is doing it like this. You know what it is doing in general, but not specifically. And that's why the test data set is so important, to test the accuracy of your algorithm, if it's useful or not. A particular machine learning approach is neural networks. Here you have some nodes. Here you have the input layers. And here you have the output layers. The input layers can be the voxels of a 3D image dataset, and the output layer can be, for example, the probability that the object belongs to a specific class. And then you have hidden layers in between. And if you have a lot of hidden layers, it's called a deep neural network, and it's called deep learning. And the arrows symbolize weights. And basically, this node contains the linear combination of this weight times this input layer, this weight times this input layer, and this weight times this input layer. And
we don't see the arrow, so you can say the first.
Okay, yeah, okay, thanks. And yeah, since this is all a linear combination, if this would be all, it would only be able to model linear functions. That's why on each node there is also a nonlinear function. It's the same for every node. You define it in the beginning. There are different options that gives a nonlinearity in all these things. This makes it really powerful. And now we come to and what I want to say is here all the nodes are connected to all the nodes in the next layer. And if you have a huge data like an image, for example, or a three-dimensional image, this would be a lot of weights, and it would be really, really slow. So what you can do is you don't combine all the pixels in one layer to all the pixels in the other layer. It's not dense anymore in a sense, but only to the neighboring pixels. So what you have a filter, which is the vertical line and the horizontal line here. And the image is filtered, so you pass the filter through the image, and so then each, for example, here you have a 5x5 pixel filter. So all the pixels in the next layer are connected to the 5.5 neighborhood of the pixels before. And you see in the left upper image, you see it's vertically splashed, or vertically smoothed, and on the right image it is horizontally smoothed. Yeah. But there are still a lot of weights and still a lot of it's a huge dimension, so there are some strategies to reduce the dimension. For example, here what you can do, here you see it again, you have a filter size 3x3, and it is connected, the red one, for example, and it is connected to the red pixel in the output image, and the blue one is connected to the blue pixel. And you see the stride of 2, you jump 2 further. So this is a strategy to introduce a stride to reduce the output dimension, or the dimension if you have large data sets. And it's also a good regularization. Another strategy that is always done with convolutional neural networks is a pooling layer. Here, for example, the max pooling layer. There you have a pooling kernel. For example, here you have a 2 times 2 pooling kernel, and you just take the maximum value of this in this 2 times 2 area. So, for example, in this case, it is 7 would be the maximum value in the red one, and then you can also decrease the output dimension or the dimensions in the neural network. So now I show you how everything is connected to each other in a convolutional neural network. You have an input image, and then there you have some kind of a filter, or more filters actually. You have all the blue images in the first convolutional layer are from different filters. So the images are filtered. These are the images that are filtered from different filters. So the algorithm is not learning the weights anymore, but now he's learning the filters that are optimal for him to solve the given the given task. And from there, then you have a pooling layer to reduce the dimension, again, a convolutional layer, a pooling layer, and so on. You can have a lot of them just to have a really deep network. And in the end, all the remained pixels or voxels are flattened to one line. And then here we start to have a standard neural network again. For example, here we can have a dense layer to connect all the dots here to the output dot. And the output is, for example, the probability that the input relates to Alzheimer. Yeah, that's basically how to a really simple architecture for a neural network, for a convolutional neural network. And now I come to the code. First, I need to import all the toolboxes that I need. First, I have a numerical toolbox for numerical calculations, a scientific toolbox. There I need some image calculations. TensorFlow is the main toolbox that we use. This is implemented by Google and is open for Python, and you can use it to implement neural networks and deep learning, convolutional neural networks, and etc. Pandas is a kind of a database toolbox to handle databases, and SimpleITK is also imaging toolbox to, for example, import images and transfer them to Nifty format, for example, and yeah, some other things. And this is actually the CNN architecture that I want to introduce for this seminar, because it has a reasonable output and is also reasonably simple. It's there is an ImageNet competition in the internet where all the new architectures are competing to each other, and this is the winner of 2015 of the ImageNet. So this is a classification task for a lot of images like cats, cars, etc. And what is I want to explain you the architecture, the main structure only. We have again an image input on the bottom, and then we have a convolution layer with 64 maps, 64 different maps, and the filter size is 7 times 7, and we have a stride of 2. And then again we have the max pooling layer with 3 times 3 kernel and also stride 2. And then we have the new invention of this architecture, which are the residual units. So the idea is that you have skip connections after 2 convolutional layers. So you, at the right side, you see one residual unit, which consists of 2 convolutional layers and 1 skip connection. So you directly have a connection of 2 nodes and skip these convolutional layers and add this to each other. And it was seen that this skipping connection increases the accuracy by far. And here you also see BN right at the right, which is a batch normalization, which is also kind of a normalization to reduce the dimensionality. And you have the ReLU activation function. The activation function is the, as I said before, to get the nonlinearity into the neural network. So yeah, here we chose the ReLU function as a nonlinearity function. The activation function it's also called. Then we have a global average pool, which takes the average of every pixel in one map and flatten all the averages in the end. And here, what I included to demonstrate how to combine different datas, and I add a concatenate layer. This is for merging two different layers to each other. So here we have a completely different input, which relates to the subjects from the input image, and then I just added two fully connected layers, and then I concatenate these two layers, the flattened one from the image input and the H input from the H input. And in the end, I have a sigmoid layer, which is the output layer, which basically gives the probability that this proband has Alzheimer. Okay, this is the architecture, and here is the implementation of this architecture. So I defined a class, which is the residual unit, which has some functions. First, we have we define the activation function, which is the ReLU. It's defined on the top. Can you see? This you can see perfect. Yeah, which is here. It's defined here, and then we have the main layers, which is a convolutional 2D layer with this is the filter, how many filters we have, that one. Then we have 3 times 3 dimension, and we have strides equal to strides. Yeah, and strides is 1 here, and we have padding. I didn't explain, it's not so important. Then we have a batch normalization. We have the activation defined here. And then we have another convolutional 2D layer. And here we have the skip layers. So, and here we have an exception if strides is bigger than 1. I will show you here there is one issue where you see that at the lower violet box has a 2, so this is just an exception for here. And here it is called. We call the main layers, and here we give the inputs, and then we call all the layers recursively to each other to have all the residual units next to it after each other as layers. And in the end, we just add an activation function and add the skip layer to the set layer here, which was here the adding that you've seen. Okay, and here the model is built. So this was just the residual unit, and here we have built the whole model. So we again start with the convolutional 2D, batch normalization, an activation, and a max pooling 2D, as we've seen before. And here are the filters that we use. So we use 3 times 64 maps. After that, we use 4 times 128 maps. After that, we use 6 times 256 maps. And after that, we use 3 times 512 maps. So we see this is really deep already. So we have a lot of residual units next to each other. Here we are calling the residual unit class. We give the filters that we just we give the special filter here, and we give all this filter in a for loop and add this to our model. And then in the end, after all these residual units are performed, we have the global average pooling and the flatten layer here, and update our model, always giving the layer before to update and add this to the layer and add this to our model. Here comes the second fork, the H input. So here we have the H input. The shape is 1 because we only have one H per individual. And we add 2 dense layers with 30 nodes. Activation function is again the ReLU function. And here we merge the layers. So we use the concatenate function from Keras, and which uses TensorFlow actually, and merge the model, which is the image model, with the H model that we created here. And actually, this can be done to also combine different image modalities. Here, I used it to combine the H data with the PET image data, but this can also be used for combining different image modalities. And later, I will show another possibility to combine different image modalities. Yeah, and then I create the Keras model. I define our inputs, the input image and the H input, and create our output, which is the output layer defined here. And here the model is compiled, so it's given which optimization algorithm is used, and which metrics and which loss function. Yeah, here I do some pre-processing of the image. I first resize the image such that every image has the same shape. I transpose it. This is a technical thing because I need the depth of the image at the last position for using TensorFlow. And here I have a different function for fMRI pre-processing that I will use later. Because here I also have a number of fMRI images. I'm not only using one, but more. And I first normalize the images from 1 to 0, from 0 to 1. And I also resize it, and I transpose it again for this technical reason. Here there is a resizing. I resize it to, the width is 128 and times 128, and it's 47 deep. And here it's the same, but we have 47 times number of fMRI images. I will explain that later. And the normalization is normalizing it from 0 to 1. So what we do now, we load the FDG-PET images of the brain. I downloaded them from the ADNI database, and I filtered it by the following conditions. I only used 18 FDG-PET images. I only used images from the GE medical system in order to keep it homogeneous. I only used images that had this dimension, and I used the added image from 30 to 40 minute post-injection. And the sample size then with this filtering was, I had 95 brain healthy patients and 76 Alzheimer patients for our example, for our tutorial here. And yeah, then I define the paths to the downloaded images, the PET path and the fMRI path, which I use later, and also the H path. And then I load the images. I go to the right directory, and I the first image in the folder in Python, it's always starting with 0, is from 30 to 35, and the second one is from 35 to 40. I want from 30 to 40, so I added the first 2 images and append it to some list. So I have a patient list with the subject ID and an image list. And then I load the H data, which is a CSV file. I don't go into the details, I just read the CSV file with the pandas toolbox. And then use this function, I apply this function, so I load the PET images from Alzheimer and from normal patients, and I also load the age data, and then I go through all the subjects and append the age because I had age from more patients actually, and then here I just use the age from these special subjects. And here I define my input dimension. I make this list to an array that can be used for calculation, and I define my labels. So Alzheimer is label 1, get a label 1, and all the normal get a label 0. That's what I do here. Then next, I will split the data. So I define a function for splitting the data. As I said before, 60% will be test data, 20% will be validation data, and 20% will be testing data. And what I do here, I combine the Alzheimer data and the normal data, the Alzheimer age and the normal age, and the Alzheimer labels and the normal labels. And then I first combine the images with the age, and then there's a function zip that can zip the data and the labels to each other, and you have one data set containing all of the data that you need. This is provided also from TensorFlow. And then I first shuffle the data, and then I just take the first 20 as test data set, and the rest as 60% for the train data set, and then just the rest for the validation data set. And this is what is done here. This is some technical thing. We define a batch with batch size 2, so we take 2 patients in one batch, and we prefetch 2. This is that it can be calculated faster, and in parallel it prefetches 2 while it's calculating with the other one. So this is just needs to be given to TensorFlow for improvement of calculation speed. And then I call this function. I give our Alzheimer data, the age Alzheimer, the normal data, the age normal, and the labels. And the next thing is we see here we have, because it's 95 and 76, it's not completely balanced. So here are some weights in order to balance this unbalanced data set. And these class weights can be given to the TensorFlow calculations in order that he knows that he can it gives better results if it's not completely balanced, if you don't have the same class same numbers in all the classes you have. Here we define our matrix. We use the area under the curve, which is a matrix for binary is a good matrix for binary problems, and we use the binary accuracy as a loss function. And here we call the function that we created before, the ResNet34 model, and we give the input size that we created, 128, 128, 47. And model summary just gives a summary of our model, and epochs is the amount of steps that the algorithm uses to update the weights. I just used 50. Usually you can make here, you can stop when some criteria is fulfilled, or you have different stopping criteria. I didn't optimize this model, it's just for demonstrating. So I just used 50 here, and here I fit the model. So this is basically doing the training. So it fits all the weights of the model to optimize this special task. I give the training data set that I created. I give the validation data set for showing the validation values. I give the number of epochs, and I give the class weights that I had before. So here is the output. I'm not able to calculate it on my computer because I don't have a graphical programming unit. But actually I can run it, but it's very, very slow. I will run it in the end, and then I can show you how it runs and how you do it. But here I pre-run it on my graphical programming unit at home. So here first there is the summary. We have our input layer. We have our convolutional 2D layer. We have a batch normalization, an activation function. We have a max pooling layer, and then we have all our residual units that make it very, very, very deep. Here we have the input layer for the age. We have a global average. Now it's not in order anymore. Here you see this takes the residual unit from 47 from above. This input number 6 is then going to dense 6. This dense 6 is going to dense 7. And this dense 7 is going to here to concatenate. And here in between there is the global average pooling from the other fork and the flatten from the other fork. And these two are then concatenated as we expected to one layer, and this goes to one dense output layer. And here's the output of the training. So we have 50 epochs. We see we have 3 seconds per epoch, more or less, on the graphical programming unit. We have the validation loss on our validation data that is not used for training. And yeah, here we have the here we have the validation area under curve and the validation binary accuracy for all the epochs. So we see when we have a look at these values and these values, this should be increased. And in the end, yeah, we have 72% or 0.72. 0.5 would be complete random, and 1 would be a perfect match. And yeah, here it's not perfect, but it's not nothing. So yeah, we didn't optimize it, but it's still giving a reasonable result. And on our test data set, we have an AUG of 0.64. And here we can see the confusion matrix that it says, okay, 21 are correctly predicted as Alzheimer, no, as normal, and they were normal. 4 were correctly predicted as Alzheimer, and they were Alzheimer. 6 were wrongly detected, they were Alzheimer, but they were predicted as normal. And here 3 were predicted as normal, but they were Alzheimer. So it's not perfect. But yeah, it gives some, it goes in the right direction. I think with tuning of hyperparameters, we can get a better result. And we can also change the step length. I just used the standard definition, so there's options, but I just for showing that I didn't do this. Now we go to fMRI images. So we're using only the probands that also have fMRI images, and the sample size of probands that have FDG-PET and fMRI images and fulfill my previous conditions, then we only have 70 brain healthy probands and 47 Alzheimer patients. So this is now a trade-off. We use more data, more image modalities as input and have a broader input, but we have less probands, so a smaller sample size. And here I used the different approach. I didn't use the concatenate to combine these different things, but I just added the 3-dimensional voxel images just to each other in the 3rd dimension, in the width. So what I did, I ensured that that they also have the same shape, 128 times 128, and also I made them the same shape at 47. So in the whole, I have one huge 3-dimensional data set with 128 times 128 times 1 for the FDG-PET, plus the number of fMRI images, times the 47, that is the depth of one of these 3-dimensional images. And one of these yellow boxes is 1 time slot of the fMRI. And here for demonstration, I just used the first 10. Probably it will be better to to use more, but this is, again, the goal here is not to get best results, but just to demonstrate how it works. So I used the first 10 time slots of the fMRI images, and here I load the fMRI images, the first 10. I don't go into details. Here I go through all the patients from the Alzheimer patient list to have all the fMRI images in order to later get only these images from the FDG-PET and also only the age values from this FDG-PET, just to ensure that they fit together, and I only have the patients that fulfill all the have fMRI, are listed in the fMRI list and also in the PET list. Then in the end I have the Alzheimer data again, the normal data. Here I do the combining of the images. I combine the Alzheimer image list, only the indices that have fMRI PET, and I connect it to the fMRI images. Here I do the same for the healthy patients, and here I define the input dimension as I've shown before, 47 times the number of fMRI images plus 1. And here I create the Alzheimer labels and the normal labels again. This is the same as before. I again create the weights that are a bit stronger now, because it's the difference is bigger in the class weight, in the class numbers. And here again, we build our model. Now we have another input dimension, because we also have the fMRI images. I also have to get the summary, and I fit the model. So I calculated I trained the network. And here again, this is the same because it has the same structure, the model. Here again, the epochs. Now it takes 9 seconds for one epoch. So because it's a bigger input image, because we also have the fMRI images. And in the end, we see here, again, we have a look at the validation AUG, which is 0.81, 0.71. So here we see there is a huge variation still. So probably it would need more epochs here. So usually I would try it now with more epochs to get better results. But anyways, we will have a look at the test dataset. And here we had an area under curve from 0.71, so it was comparable to the other one. And here we have 0.68. It's a little bit better than without the fMRI. We have to take in mind that we have less probands now. And here we see we have 10 correctly predicted as normal, and 5 correctly predicted as Alzheimer, and 4 wrongly predicted and 3 wrongly predicted. So it is a slightly better performance than the other one, but still possible for improvement. And now I can show you. I will. I didn't say in the beginning. I use a Jupyter notebook, which gives you the opportunity to put images, text, and code into one, and even run the code in Python within this Jupyter script, which is quite nice for tutorials, or if you want to keep track of what you did and have the outputs. And now I will show you how to run. You go into the box, and then you can put Control and Enter, and then you run this box. This doesn't have output. I just run now all the boxes to show you. I need to run it because I want to show you the training. Oh, it has an error now. Oh, I changed the path. My
Because it wasn't this computer where you did it first.
Yeah, exactly. I was on another computer. Wait, maybe I can solve it fastly. Wait here. I think I already changed it. Another one because I tried it. Just the same. Where are the paths? Sorry. Here. Yeah. Here I should have changed it already. So I will use this one for demonstration. Yeah, it's working. I run that, and I also run that, giving the output. And now we do the training. So I do run this. And okay, the summary is already given. And remember, it was 3 seconds per epoch. And now because without the graphical programming user interface, it will take probably around 30 seconds per epoch. So yeah, it's 10 times slower, but just for demonstrating how it looked like and how it goes through all the epochs.
If you want, we have a question.
Yeah,
while we wait.
Exactly. That's a good idea.
Okay, so Paolo asked, okay, very interesting. Could you repeat what do you do with the age model? If I got correctly, you have 2 layers of 30 nodes completely connected. However, the input is age, aka a number. What's the role of the 2 layers of the age model then? Mm-hmm. Sorry, I'm very naive.
No, that's actually a good question. So we go to the nodes. Here imagine, let's go here. It's just in the input you have 1 node, but then you have 30 nodes here and 30 nodes. So 30 nodes in the hidden layers and 30 nodes in the second hidden layer. So you have then 30 weights going from 1 node away, 30 weights to 30 nodes. And then you have connection from 30 nodes to 30 nodes. So you have 30 times 30 weights and connections between the nodes. And then you go from these 30, you put these 30 nodes together with the flattened from the image input and then connect all of these nodes to the output layer. I hope this was a bit clear. So you go from 1 node to 30 nodes, and again to 1 output node.
The question is more like why
okay. Yeah, because it gives more variety in the model to choose the weights, and you also have the non-linearities, so you can model complexer functions depending on the age, other than just linear or just with 1 node. So this is basically the main idea of deep networks, because then you have because the age will not relate linearly to the output. So there will be a complex function, and the more nodes you have, the more complex functions can be modeled by this network. Now we can, if there is no
for now not. If you have other questions, you can write them in the chat or just.
And if it was not answered to your that you could understand, then just ask again. It's fine. Here we see now we have it's 30 seconds per epoch, and we see that it's slowly adapting. Now we have 6 epochs already, 7 now we have 6 finished, and it slowly increases the values.
Other question? One question per epoch. So
I think we don't need to.
We need
to
30 questions
because we have seen the.
Okay, so Raja asks, hi, I have a question. You said that you have 128 by 128 by 46 dynamics. What is this 46? What is your fMRI input image? Activation image, connectivity image? So what kind of input?
What kind of fMRI image is the input? Actually, I'm not so into fMRI, so
You did any processing, so you downloaded the images?
I didn't do any processing. I just used the image raw like it was and used the first 10 time slots. Yeah, that's what I did.
It's a resting state, I think.
Yeah, exactly. Yeah, it's a resting state. Yeah, it was a resting state.
So can I talk here directly? Because by typing it's better, I think, to speak directly, so the question will be clear. Can I
Yes.
ask the question directly or
Yes,
only
yes.
in English? Yeah. So basically those fMRI images, it's minimum like a 200 dynamics always, and based on different experiment, it's some people also use like a 500. Like in our setup, in old fMRI acquisition, we have a 300 dynamics, and here we have a 500. So I was wondering, maybe some kind of what is downsample happen. And second, on what basis the PET images and fMRI images are concatenated? Because you shown the concatenation of PET and fMRI, and if I'm clear, both are different what is intensity level and different information, and I mean, how,
Yeah.
with what
Yeah.
basis you?
Yeah, exactly. So with dynamics, just to be clear, you mean I mean the 47 is the depth from a three-dimensional volume of the brain, and
fMRI
the dynamics is the in the database that I had, there were different numbers, maybe 200 and 500. Yeah, I don't know. I just took the first 10 naively, the first 10 of these 500 or 200 images. So yeah, I lose a lot of information. This is just for demonstration. This is not for getting the best result. This is just for demonstrating how to combine different image modalities. That was the aim of the talk. And so I just used the first 10 of the dynamics.
But let's say if you want to combine different modalities, do you have to do any pre-processing to make images similar in terms of the dimensions, yes, in terms of intensity? What is the kind of preparation that you have to do?
Yeah, that can increase the. I did normalize from 0 to 1 the fMRI images, and the PET images. Yeah, I there have the counts, so it's a bit more. So they were not so far apart from each other in the range. But yeah, if they are too far apart, they need to normalize to each other. Yeah.
If I have a time, 1 minute again, another small question.
Yeah.
Or we have time for the okay. So additional to the accuracy, I mean classification of between two groups, do you do this? Your approach also allows to look which features, like which brain region or which network is responsible to classify these two groups?
Which region of the brain? No, it doesn't. There is a way, a really new, called the vision transformer. That's 1 year old, also implemented from Google. And I think this can a little bit see which region gives the most, is most important for the algorithm. I think the ResNet is not able to do it, or I don't know it. I didn't do it here, and I actually never did it before. So yeah, this is done here.
Thank you so much. Thanks a lot for your all this.
You're welcome. Okay.
So should we check? No.
So
we will just go ahead forever.
Yeah, I think we can see a lot. I just wanted to demonstrate how how the epochs are, and how just to see that how it runs. I don't think we should wait until the end, because we've seen already the result. Yeah, so that's it from my part. If there are no more questions, thanks for attending.
I think no. There's one more. You want to come here or you want to your microphone, or you can come here. So we have a question for Glenn.
So this thing is obviously more about prediction and it is about interpretability. But do you have anything to say about how you could transform this into more interpretable measures? Like I see that for Alzheimer, age is very probably predictor as well, I think, than the brain images. Do you think that you can at some point even separate these? Like, okay, we see that age predicts like most of the variants that we explain in the model, and not really the
Yeah, actually, because age comes very late, we can have a look at the weights in the last layer, because and then we can see if the weights from the 30 age nodes are higher or more important than the weights from the other. Since this is just the last layer we have to look at, actually this could be possible, and another approach can be to train it without age and train it with age, and then we see if there's a big difference. Yeah, these can be the two options too.
Okay, great. And also, then expanding on that, you now concatenate the PET images and the MRI images, but then there's no way, I guess, to really separate these anymore to create a more interpretable thing anymore, right?
Yeah, no, there's not.
Just pure prediction.
But anyways, if it goes through the ResNet, I think, because there are so many residual units in between, such that the interpretability is anyways lost, because there are so many weights that it's impossible to be able to interpret.
Do you think this is not an important question to maybe separate these two kind of modalities?
Yeah, it can be an interesting question, but then I would use the second approach, such that we use it without fMRI and with fMRI, as I did, and compare the results. Yeah, that would be the way, because it's not interpretable anymore, because it's.
And then would you then compare it like the AUC for both things, and then?
Yeah, for example, which is not perfect, but it's the best that we have. Yeah, that's the best.
But so you show that, for example, for the model based on fMRI and FDG-PET, you had a lower amount of subjects, so the subjects are not the same. So to make the models comparable,
we should reduce also the amount of the sample size if we have only the PET images.
Exactly. Yeah. And maybe some cross validation there.
Exactly. Yeah.
Oh, thanks.
You're welcome.
Are there any other questions? Okay, and by the way, this code is available for sharing, or
not yet, but I think I can. I think I can. We can upload it because it's
a minute or no?
Sorry.
Do we have another 1-2 minutes?
Yeah, we can. Yeah.
So deep learning always depend on the data number of amount of subject or amount of data we give. So here also I see you have used a small amount of data, like 30 subjects. So how you handle the data, or how you manipulate to enhance low amount of data to high amount?
For this tutorial, I didn't manipulate it all because I wanted to keep it simple, but there are possibilities such that you can turn the image and also use this as an input, or to resize it and have this as an input, and and also to because if you turn the image, it should be still the same brain, and these are possible things to increase the amount of sample size if you have a really low one, and want to improve the output. But I didn't do anything here in this case because I wanted to keep it simple.
And we have another question by Paolo. If Raja, you're satisfied with the answer, or?
Yes, thank you.
Okay. Okay, Paolo asked another question. How do people design different architectures? What is the rationale that is behind creating a new one or this one? Craziness.
This is the main point, how to be creative. It's a big question, philosophical question. But I can explain the intuition behind this one a bit, or at least give a guess or a hint. Here you the skip connection. the weights can be also considered as the negative weight. So mathematically it's the same because the weights can be positive or negative. So you can think about this plus as a minus mathematically.
The plus on the right.
The plus on the right, where you add the skipping connection and the convolutional connections, and then you have kind of a residuum, kind of an error that you do, or kind of a what you do different, how you change this value by the two convolution layers. That's basically what you calculate with this plus. So basically, it's giving you give the changes of this convolutional layers, and the idea was that giving the changes or the residual can be better than giving just the output. It can has more information, and that was the intuition behind it. That's why they tried to implement this. Yeah. And how you make different architectures. I think everybody wants to. Yeah, you want to win the ImageNet competition. Yeah, that's a big question. I think everybody wants to invent new architectures. Yeah, that is doing research in machine learning.
Okay. If there are no other questions, cool. Okay, I agree, Paul. So thank you, Andreas. Then for the Comma Science group, we will have another seminar again by Andreas. So I suggest to take a 10 minutes break, and then we try to fit in 45 minutes, so we ended 4 anyway.
Yeah. Okay.
So, okay, thank you very much for attending, and to Andreas for the nice lesson. Okay, bye-bye.